Today we're going to talk about self-similar sets. Our previous video, remember, discussed types of counter constructions which were not necessarily self-similar, so those results are not a subset of the results we're going to discuss today, so check out that video as well. What we're going to do is give a mathematical definition of what self-similarity is, and then talk about a theorem which gives sufficient conditions for certain sets to be self-similar, and then calculate the dimension of those sets based on how they are constructed. So to motivate the discussion, we look at the four-corner counter sets. I hope you can still see these quite not so visible dots here and there. That's in fact how counter set looks like. Now, the self-similarity is intuitively the fact that there are these four subsets, parts of the full set, which nevertheless look very similar to the whole piece, to the original set. So each one of these is just a copy of the original large piece. And that is the intuitive meaning behind self-similarity. But mathematically, to make it precise, we can do as follows. Think about four maps from R2 to itself. The first map is just multiplication by 1/4. What this map does, if you're familiar, which you definitely are, with vector calculus, so any point can be seen as a vector, so this will divide it by 1/4, and 0 goes to 0, so everything is centered still at 0. S2, for instance, is the same map, except then after that shrinking, you shift it upwards by 3/4. So 0, 0 gets mapped to this one. And S3 will shift 0 to here, and then S4 will shift 0 here. Other than that, they all just shrink everything by 1/4. So if you apply S1 to the set K, the counter set, S1 of K will be exactly this one box back here. So let me get rid of these. So S1 of K will be the part of counter set precisely that is here. And S2 of K will be this one, and so on. So self-similarity can be given by this condition that union of images under these Si, their union gives back the full set. So the theorem, the general theory that we're going to discuss, and which is, by the way, due to Hutchinson, and the proofs, I'm following Mattila, but the proofs are not included there, and the proofs are referred to in the book by Falconer, if you're interested in finding proofs. So the general theme is that not just for these particular maps S1 to S4 that we had, if you have any number of maps, you will have a unique compact set which satisfies this condition, which we say is invariant under these maps. So starting with Si, there is always one and only one compact set which is closed under this operation, that if you apply these scalings and then put the images back together, you recover exactly the set you started with. We will see that you don't need to know K beforehand. In fact, you can start with these scalings, any number of them, not necessarily 4, and then there is a way to construct and reach this set K through some iterative operations. And since K is determined by these maps S1 to Sn, we must also be able to recover the dimension of the set. And indeed, there is some very explicit formula that we will see. In this particular case, because all maps have the same shrinking factor, have the same scaling factor, it's given by this formula. The number of maps you have divided by inverse of the scaling ratio. So in this case, we have 4 maps for the 4-corner Cantor set, and then each one was dividing by 1/4, so you get 1. And previously we had seen through very different techniques that the Hausdorff dimension of 4-corner Cantor set equals 1. So we have to be a little bit more careful, because if you start with any random choice of S1 through Sn, it is not necessarily the case that their images are completely separated from one another. So let's take care of that. First of all, we define a similitude to be a map between a Euclidean space to another copy that scales the distances by exact factor of r, where r is strictly less than 1. So in particular, it's shrinking. But this is not an inequality, so it's not just a contraction, it's a precise formula for how distances behave. So if you have any 2 points in the domain, in the image, their images, wherever they map, will have a distance that is r times the distance of the points in the domain. This is true for every pair. From this, we don't even begin by assuming that S is linear or anything, but it turns out that this condition, this distance condition, is very strong. It forces S to have this particular form. It's a translation to a new point. So origin goes to x0. It's kind of x0 is the new origin. So that's the shift part. And when you ignore that, which is a simple operation, the rest is multiplication by this r factor, which is a scalar, and then a matrix. And that matrix is in the orthogonal group. So it's not just any matrix, it's an orthogonal matrix. So geometrically, orthogonal matrices are those matrices that do not change distances. They are isometries. For example, if we look at R2, the linear maps that do not change distances are rotations. So maybe this goes this much and then this goes that much. But also reflections. So the other kind of maps are reflections there. So in Rn, of course, they are a bit more complicated than that. So in some subspaces, it can reflect and whatnot. But all in all, this is telling us that the structure of similitudes is pretty simple. They are basically n-dimensional rotations or reflections, then scaled by the constant factor r, and then shifted. We won't need any facts about orthogonal matrices or anything. Okay, so the first theorem claims that if you start with any collection, any finite collection of similitudes, so the only restriction was that they scale distances by a constant factor, each one with a different one, so this could have R1 and this could have Rn, not necessarily equal, then there exists a unique non-empty compact set K, which is invariant under these. That means if we map K under each of these similitudes, and then we take union, we recover back our original set K. Of course, the four-corner example that we just saw is with n equal 4, and each one was a similitude by factor 1 over 4. We'll see a surprising fact, but I want to keep it for after we discuss the other theorems about how you can actually find this K. How do you, beginning with S1 to Sn and having no idea where this K is, how would you recover it? Okay, now we come to that comment about images of these. So we like to think in terms of the four-counter set that, well, S1 takes the unit cube to this one, S2 to this one, so they are perfectly separated images. So S1 of K has nothing to do with S3 of K. They are completely far away, and that's the simple picture we like to think in terms of. However, per se, in this theorem, we did not assume anything about whether these pairwise have any intersections. And that is good because that makes the theorem even more interesting, that even if you have that kind of overlap, it doesn't ruin existence of such invariant sets. But of course, for the purpose of calculating Hausdorff dimension and things, and also intuitively, we don't want to call sets with such overlaps, bad overlaps, self-similar necessarily. That's why we define a set to be self-similar. So K is as above, so you have a bunch of similitudes. Then K is the unique invariant set for them. But that doesn't make it a self-similar set unless we have this condition that, well, K has some dimension. We don't know that yet. We will soon. So we require that effectively the images of different similitudes are separate. So they may technically intersect. So as sets, the intersection may be non-empty, but it will have 0 S-dimensional Hausdorff measure. And because our K is S-dimensional, that means effectively K doesn't care about those tiny overlaps that may happen. So if we have this effective separateness of individual images, then we call the set K self-similar. But before finding this K, it may be difficult to tell when you will have this condition for negligible overlaps. And that's where this other theorem comes in, and it gives a sufficient condition for when you will have a self-similar set. And that condition is interesting because if you look at the statement of this, the assumptions have no K in it. So until this line, there is no mention of K anywhere. So these are assumptions. Then you see that the self-similar set, the invariant set will be self-similar. So what is this condition? It's called the open set condition. And it says that we have a non-empty open subset of our N, not necessarily bounded or anything, just non-empty, such that, well, each of the similitudes map O into inside of O again, so it doesn't seep outside of O. So this is your open set O, and SO, SI of O, will map it. So let me make a copy of an approximate copy of, well, I can actually literally make a copy. Okay. Sorry about that. Okay. That wasn't the easiest way to do. Okay. So that is the set O, and we will have that Si maps O into something that is in the interior of itself, and that is for every single one of them. So maybe Sj of O will be this one. And actually my picture here is accurate because the second condition is that they have, not in the sense of measure, but precisely and honestly, they are non-overlapping. So you assume that there is some open set. Initially, you don't assume it has anything to do with that counter set. You're not even aware of that counter set, that invariant set at the end. But you know that there is some open set with this condition, that these SIs map back into the set O, and pairwise the images are disjoint. If you have this condition, again the so-called open set condition, then the invariant set for the similitudes will be self-similar. And definition of self-similar back here. Okay, let me we talked about several things, so let's probably look at an example. This is the Witschek set, named after mathematician Witschek, pronunciation according to Wikipedia. So it looks like this, but how do you construct it? The self-similar construction will be that you begin with the unit cube, unit square, well, two-dimensional cube. Then you will replace it by the 5 dark squares. So what is a self-similar construction through similitudes here? So the first similitude will be that S1 will be just multiplication by 1/3. So notice that the scaling factor is not the volume or area, which will be 1/9. It's the distance scaling. So 1 maps to 1/3. And similarly in the other direction. So image of S1 will be the first dark square here. Here, that's S1 of the whole square 0, 1 squared. And then the others here, here, and here, these squares will be S2, S3, S4, and S5, which are 1/3 of x plus the right amount of shift, which will be 0 going to the bottom left corner. Okay, so those are the similitudes with the ratio 1/3. And then if you repeat that process, now you look at this whole picture and then you apply S1 up to S5 to this one. So that means you will have copies of the rescaled copies of it placed into 5 positions, here, here, and here, and here. And then you will have a scaling of the whole thing again, and then you will place it into the 5 corners, and you repeat this ad infinitum. The limit that you will get will be your Witschek set. This one has a difference from the 4-corner set because this time around, the images under similitudes are not technically disjoint, but they have this condition for self-similarity, that they may intersect, but the intersection has 0 S-dimensional measure. So whatever this set is, its Hausdorff dimension is not 0. So S is bigger than 0. That's why HS of a single point is 0. So for example, this will be a 1, say S3 of K, and then if this is S4 of K, the two will intersect here at one point. So these could be empty, for example, if you consider this versus that, in which case even better, or they will have at most a 1 point intersection, in which case HS is 0 nevertheless. And that means the resulting invariant set is self-similar by definition. We could also see that by the open set condition. If you take the interior of unit squares, so that means you exclude the edges, and you take this to be O, then open set condition is satisfied. And I leave that to you to just visualize how. So also this theorem then predicts that the resulting set is self-similar. Okay, now finally we come to the promise that we will know the Hausdorff dimension of this self-similar invariant set just from knowledge of the similitudes. Under the open set condition, the theorem reads, again due to Hutchinson, the Hausdorff dimension of the self-similar set, necessarily self-similar because we saw previous theorem gives this, set K that we get from these similitudes is given by this unique real number which satisfies these. So what is Ri? So Ri is scaling ratio of similitude Si. So if you just know, you don't even need to know the rotation part of Si. All you need to know is how they scale down distances. Then you put these numbers and you raise them to power S. You add all of them. We have n many of them. And for example, by intermediate value theorem, continuity argument, you can prove that there is some S for which this is satisfied. And that S will be the Hausdorff dimension of the self-similar set you have. Moreover, the Hausdorff measure of set is actually positive and finite, which we always like. And there is also a regularity part to that, which says that the this measure, HS measure, is distributed quite equally throughout the set, and that is not surprising if self-similarity is anything at all. That so this is similar to Alford's regular condition, except we have this condition on radii. So this is saying that if you place a ball of radius r centered inside your self-similar set, then the HS measure of part of K that lies within that is basically like power of r to power s. So up to some constants which do not depend on the point x or the radius r. So again, this is a very desirable condition for Hausdorff measure of sets. Okay, the corollary from this will be that if all ratio is just the same value r, then the Hausdorff dimension is, so you can, this will become n times r to power s, and if you just apply a log, you will see that this will be, this has to be log of n over log of 1 over r. So for this Witt-Scheck set, so we have 5 similitudes, and all of them had the ratio 1/3. So that will be the Hausdorff dimension of this Width check set, which is strictly bigger than 1.